So stepping way back here and thinking about the atoms that build all biological molecules, we want to think about where we get those atoms. So if we think about 5 really important atoms that we have that we build things from, we've got carbon, hydrogen, oxygen. That's how we make our carbohydrates. We add in nitrogen. I should say carbon, hydrogen, oxygen really are, carbon and hydrogen are our lipids, carbon, hydrogen, oxygen are our carbohydrates, carbon, hydrogen, oxygen, nitrogen, we're going to be building up our proteins, and then once we add in phosphorus, then we're going to have all 4 of our biological molecules, including our nucleotides. Okay, so if we think about where we get these, right? And we're going to think very simply about their elemental sources. Carbon really fundamentally at its core comes from carbon dioxide. Nitrogen at its core really comes from nitrogen gas. Hydrogen comes from water. Oxygen comes from oxygen gas. And then we've got phosphorus really comes from phosphate. Okay, so I want to highlight that with the exception of phosphate, these 4 guys are all found atmospherically. So these all are gases in the air. So a pretty easy and readily available source. But the reason I've drawn this diagram the way I have is these guys are particularly problematic. So these guys are problematic. And here's why. So if we were to draw structures of these, here's carbon dioxide. Hopefully everybody's good at drawing Lewis structures of molecules, particularly these simple molecules. And here's nitrogen. These are fairly unreactive. Okay, so we've got a nonpolar molecule with carbon dioxide. Okay, and with both of these, we have strong bonds. So that doesn't make them very useful sort of building blocks to build all the molecules that we need. So a way to fix that is to have enzymes that can take both of these fairly unreactive molecules and put them into bioavailable forms. Okay, so I'm going to zip down here to the bottom just to highlight, here's the important way that we're able to do this. When I say we, I mean sort of as a living sort of earth. We as humans aren't able to do this, but if we think about the biochemistry that's happening right here, this is carbon dioxide assimilation by the enzyme Rubisco. So thinking about what's happening here, right, we're going to have carbon dioxide that we have in the air, and we're going to be making it into carbohydrates that are fuel. Okay, the enzyme responsible for doing this is Rubisco. Okay, and so we would not be able to have fuel in our life if we didn't have plants that were able to fix carbon dioxide as fuels using the enzyme Rubisco. So just highlighting in a little review here, we actually are able to take carbon dioxide and make it into a semi-bioavailable form because we're able to convert it into bicarbonate. And the enzyme, right, responsible for that is carbonic anhydrase. So carbonic anhydrase. But importantly, we cannot convert bicarbonate into fuel. So we can't use bicarbonate as a way, for example, to do gluconeogenesis. Okay, so Rubisco is a key important enzyme for making bioavailable carbon. Okay, taking carbon dioxide, which is unreactive, and converting it into a bioavailable form. So key here is that carbohydrates as fuel are bioavailable. Okay, and so this really is what is referred to as the carbon cycle. Not specifically the Calvin cycle there, but the ability to take carbon out of the atmosphere, make it into fuel, right? And then metabolism takes that fuel and returns it back to carbon dioxide. So what we have up top here is then the nitrogen cycle. And so in a much similar way, there are organisms and enzymes that are able to take the fairly unreactive atmospheric nitrogen and put it into a bioavailable form. So this is what we're really going to be talking about here, is the enzyme nitrogenase. Okay, so that's the key piece here, is we are going to take nitrogen, again, fairly unreactive, and we are going to have nitrogenase is the enzyme, convert that into ammonia, which is important because that is a bioavailable form. So often there are plants that are called nitrogen-fixing plants, but it's not because the plants can fix nitrogen themselves. Really, there are nitrogen-fixing bacteria that live with those plants, and they are responsible for sort of being able to do this biochemistry. So one of the take-homes that I hope you have from this how to get your atoms piece is if we didn't have bacteria that could fix nitrogen and plants that would fix carbon, we would not be able to live on the planet as we do.